Took a shower.
Okay, we'll get started here. So you guys should have all received an email from me regarding your test grades and your current grade in the class. Anybody not get that or anything? Okay. Yeah, I'll take your homeworks, your labs here. You can send those in. So I know some of you had some difficulty with R and all of that. The key being, yeah, just put it right there. That's fine. It was not my intention to make your life miserable or anything like that. Okay. The truth is we should probably use the computer more than we actually do for this class. But just the format of us meeting for lecture is not conducive towards that kind of lab style thing. Statistics today is almost entirely done on the computer. Very little is done by hand, so I would feel like I was not doing my job if I taught this entire course without you guys using the computer. And so I do have that component, but I also know that it can be frustrating, especially if you're new to coding and computer programming in general. Just computers are very, very picky. Things have to be exactly as they need to appear, otherwise they get confused. Anyway, I'll take a look at what you guys have turned in, and we'll go from there. Okay. So today we will continue our work in Chapter 7, and we'll also just touch on Chapter 8 briefly. I think that's it. This is all on hypothesis testing for the means from two samples, two independent samples. Okay. All right. So last week, when we left off, we left off in Chapter 7, just kind of giving us a general idea behind a hypothesis test. Okay. So we have a null hypothesis and an alternative hypothesis. And when we are talking about a t-test for the comparison, that means two independent samples. So the null hypothesis would state that the population means are equal. Okay? Could also be written that is what the null hypothesis states. And we are assuming the null hypothesis to be true, and we do some calculations for a p-value, which is what is the probability of observing our data, or something more extreme, if we assume that the null hypothesis is true. The alternative then states something like the means of the populations are not equal. This could also be written it's not equal to 0. is true, then x1 bar is expected x2 bar. Okay, but of course, when we observe our samples, x1 bar will equal something, will not be exactly the same. The same as an x2 bar, okay? And so we observe a difference. And that the value of the difference is x1 bar minus x2 bar. Oh, or your book uses y bars, but sorry, I've been using x bar. I hope that's not too confusing. Okay, I apologize. I just realized your book uses y bars, and I've been using x bars. Equivalent in the idea here, okay? So when we observe our samples, we're expecting x1 bar to be pretty close to x2 bar, but of course they're not going to be exactly the same. Even if the null hypothesis is true, those two, when you take two random samples, we're expecting the means of the samples to be close, but they're not going to be exactly the same. So is the difference that we observe between x1 bar and x2 bar significant or not? Again, that's our question. Okay, and so to answer that, we look at the size of that difference versus the standard error. So, we compare, or we take the ratio between this difference and the standard error. So we get something, we call this our test statistic. And we divide it by our standard error. So the standard error is going to be the square root x1 squared over n1 plus 2 squared. So we get that test statistic. Okay, and then so if that ratio is large, is large, that means our observed difference between x bar 1 and x bar 2 is large compared to the standard error. Okay. And that would probably give us reason to believe that this result, x bar 1 minus x bar 2, okay, is not a result of random chance alone. Not a result of random chance alone. While mu1 minus mu2 equals 0. Okay. It's possible. It's possible that the observed difference, x bar 1 minus x bar 2, it's possible that that's a result of random chance, and the mean population means are actually the same, that there's no difference between them. But if that difference is large, it would give us reason to believe that it's not a result of random chance. Okay. On the other hand, if the ratio is small, then we can't ignore the possibility that mu1 and mu2 are equal, and that what we observed is a result of just the random nature of sampling and whatnot. Okay. So it's all just, is the difference we observed, is it statistically significant, or is it not? Do we have reason to believe that our null hypothesis is wrong, or do we not have enough evidence to reject that notion? Okay. So as we do a hypothesis test, okay, we're always asking about what is the probability of observing our data, or something more extreme, if we assume the null hypothesis is true. Okay, so just remember the definition of a p-value is equal to the probability Okay, so with that in mind, let's try an example for our t-test. Okay. But before we get into actually conducting a t-test, let me teach you how to use the t-table. Okay, so you guys already have the t-table. We passed it out, and we've already used it for the calculation of confidence intervals. And let me just teach you how to use it to get tail probabilities, tail areas. Okay. So the notion is this. t-distribution looks a lot like the normal distribution. It's just a little bit wider. Okay, so it's like someone took the normal distribution and sat on it a little bit and it got squished out. Okay, that's what the t-distribution looks like. And the t-table, it works very differently from the normal table. Okay. First of all, we have different rows corresponding to different degrees of freedom. So you pick a degree of freedom depending on how the problem is written, and that's basically the only row that matters. Okay, so for a certain problem, it's just once you have the appropriate degrees of freedom, that's the only row that matters. So let's say we're doing a problem where we have 18 degrees of freedom. Okay, so I'm just going to copy the numbers from the row that says 18 degrees of freedom. And we'll see at the top it says 20%, 10%, 5%, 4%, 3%, so on and so forth. And for 18 degrees of freedom, the numbers that we have in that row are 0.862, 1.330, 1.734, 1.855. And 2.007. And this is the idea here, okay? So we are centered at 0, and the notion is that if I were to draw a line, go out to 0.862, and draw a cutoff line at 0.862, and I shade everything to the right, the amount that I would have shaded is equal to 20%. Okay. So if I draw a line at 0.862, the amount I have shaded is 20%. If I go further away from 0 to 1.330, and I shade everything to the right of that, the amount that I've shaded, everything to the right, would be 10%. And so the farther we get from 0, so as our, they call these critical values of the t-distribution, as our critical values get larger, the amount in the tail gets smaller. Okay, does that make sense? So if I drew if I wrote my critical value was 0, what would my upper tail probability be?
50.
50%, right? 0.5. So if I draw a critical value at 0, I would have 50% in the tail, okay? But of course, that's every single number that would be boring, or for every single degree of freedom. So we, the table just selects certain tail values and gives you the corresponding degree of freedom. Okay. What if I don't draw a line at 0.862 or 1.330, but what if I drew a line at 1.0? Okay, so I'm drawing a line somewhere in between 0.862 and 1.330. I'm drawing a line at 1.0. How much would I have in the tail? Okay, well, our short answer is we don't know the exact value, but it's going to be between 10% and 20%. Okay, so all I'm going to say is my tail area is less than 20%, but more than 10%. Is that okay? So if I'm drawing a line at 1.0, I don't know exactly how much I have, but I do know it's more than 10%, but less than 20%. I want to make sure that makes sense to you guys. If we're at 18 degrees of freedom. Okay. All right. So when you're doing your problems, we're gonna be calculating t values. Okay, we're gonna use our when doing a t-test, you're gonna get a test statistic which corresponds to the t-table, and almost all the time you will not get one of these exact critical values. Okay, which means you will not have an exact tail area. The only time you can say I have 4% in the tail is if your critical value turned out to be exactly 1.855. Okay? If it's different from that, then you won't have exactly this much in the tail. So if you get 1.9, all you can say is that, well, I'm going to have less than 4% in my tail, but more than 3% in the tail. Does that sound reasonable? Okay. So very rarely will you get exact values for the tail area. It's only if your test statistic ends up being one of these critical values. Otherwise, you're just going to say the amount in my tail is going to be less than some number, but more than another number. Yes?
And then for degrees of freedom, do you just round it?
Yeah, so for the degrees of freedom, we're going to just use our rule of thumb, which is n1 plus n2 minus 2. Okay, that's what we used when we were doing confidence intervals. We're going to do the same for this problem here, or t-tests. Okay, are we okay with the use of the t-table? What if I said my critical value, or the test statistic, is 0.3? How much do I have in my tail? So if I'm drawing a line at 0.3, what would I say? The amount in my tail is
between 50 and 20.
yeah, over 20%, but less than 50%. Okay. Is that okay? So if my critical value is 0.3, 0.3 is smaller than 0.862, so I'm closer to 0. And so that means I have more than 20% in my tail, okay? But I'm always going to have less than 50%, unless I'm at 0. Okay? At 0, I would have 50% of the tail. The t-distribution is symmetric, so sometimes you have to look up a negative t-value. Okay? And because it's symmetric, you can just ignore the negative sign. And instead of shading to the right, we would be shading to the left. Okay. So we go to negative 1.33, then the amount shaded to the left of negative 1.33 would be 10%, okay, because it's symmetric. And that's how we use the t-distribution, the t-table. So it's different from the normal table. The normal table, you look up your z-score and it gives you an area. Here, we're doing something similar, except the areas that are given to us are, they only give us a handful, rather than a large list. Okay, so let's try out a problem. Okay, so let's try out a problem. Okay. Let's say we have a male mice weigh a different amount let's say we have sample 1, and let's say we have sample 1 will be the male mice. Let's say we have 15 male mice. The mean, sorry, switch back to y's. How much does a mouse weigh? Okay, let's say for this breed of mice, we'll say 122 grams. And the standard deviation is 9 grams. Oh, sorry, standard deviation approval. Sample 2 will be the female mice. Let's say we have 13 of them. Y bar 2, 117, and the standard deviation 10 grams. So our observed difference between y bar 1 minus y bar 2, we have an observed difference of 5 grams. We want to know, is this difference of 5 grams statistically significant or not? Okay. So we will set up our null and our alternative hypotheses. So the null hypothesis states that the two groups of mice have the same mean, or that there's no difference between the means. And the alternative says that there is a difference between the mean. There is a non-zero difference between the means of group 1 and group 2. If the null hypothesis is true, then that means this 5-gram difference we observed is merely a result of the random sampling process. Or the alternative could be true, and that there is actually a difference between the group's average weight of a male mice and average weight of a female mice, and so random sampling plays a part in that, but part of the reason why we see this difference of 5 grams is because the populations have different means to begin with. Okay, so those are our two possibilities. Maybe there's no difference, we see a difference of 5 grams because of random sampling, or there actually is a difference, we see a difference because of random sampling, and the fact that the averages are different. Okay, so we're going to calculate the test statistic, okay? And so the test statistic is we're going to see how large is this difference of 5 grams compared to the standard error. So it's going to be standard error is going to be the square root of S1 squared over 15 plus S2 squared over 13. What does that come out to be? Difference of 1.382 2. Alright, so that's my test statistic, okay? So using our approximation for the degrees of freedom, our degrees of freedom will be 15 plus 13 minus 2, so I'm going to use 26 degrees of freedom. So I have approximately 26 degrees of freedom. Okay, so at 26 degrees of freedom, what is my tail area? So just imagine I've got my t distribution, and I'm drawing a cutoff line at 1.382. How much do I have in my tail? Okay, so with 26 degrees of freedom, what would we say our tail area is?
Between 5 and 10.
Between 5% and 10%. Between 0.05, so my tail area is going to be more than 5%, but less than 10%. So less than 0.10, but more than 0.05. Or if you have them, whatever, the other way around, that's fine. Is that okay? I want to make sure everyone's okay, because so everyone's getting between 0.05 and 0.10 when we look up our test statistic of 1.32 in 26 degrees of freedom. Okay, good. So our tail area is between 5 and 10%. Okay. This is not yet our p-value. Okay. We have something called a two-sided test, all right? When we look at our null hypothesis and our alternative hypothesis, the alternative hypothesis says we are interested in any non-zero difference between mu1 and mu2. Okay, so the alternative says mu1 minus mu2 does not equal 0. We happen to observe a positive difference. In our situation, the sample 1 had a mean of 122, and sample 2 had a mean of 117. So we see sample 1 was 5 grams larger than sample 2. And we want to know, is that difference significant? So when we talk about the p-value is what is the probability of seeing our data or something more extreme. We're talking about what is the probability of seeing a 5-gram difference or something more extreme. That's why we start here and we go everything to the right. This represents 1.382 represents basically what a 5-gram difference is in terms of standard errors. Okay, 5-gram difference is 1.382 standard errors away from the mean. Or something more extreme. That's why we're shading everything to the right. Okay. The other equally interesting, though, or equally significant or more extreme, would be a negative 5-gram difference or something more negative. Because we're looking at just what is the probability of our data or something more extreme. We observe a 5-gram difference in our data. So we're looking at what's the probability of seeing a 5-gram difference or something larger, or equally unusual would be a negative 5-gram difference or something more negative. Okay. So my total tail area would include the positive and negative sides of the t distribution. Okay. So over here, my tail is between 5% and 10%. And over here, I also have a tail that's between 5% and 10%. Okay? So we have two tails. We have two tails. Okay, one is seeing a positive 5-gram difference or something larger. And the other would be seeing a negative 5-gram difference or something more negative. Both of those qualify under the statement of the probability of observing our data or something more extreme. Okay? And all of these have been under the assumption that the null hypothesis is true because we are centering ourselves at a 0-gram difference. Okay, so the total probability in both tails, or the total area in both tails, would be between what? Between 10% and 20%. Okay, so my total tail area is between 0.10 and 0.20. And that is our p-value. Okay, so our p-value is less than 20%, but more than 10%. Yay? Nay? Yes?
You were saying that the 5 is the p-value?
No. That's where this is our observed difference.
Yeah.
When we took our two samples, sample 1 gave us 122 grams, sample 2 gave us 117 grams. So we're observing a difference of 5 grams. That's not our p-value, that is just our observed difference. And we're using that to calculate our t-score, basically. It's like a z-score, but for the t-distribution. Okay. How many standard errors are we from the mean? Okay, so we go through that, and we get a p-value between 10% and 20%. Okay. So think back to what the p-value means. It's the probability of observing our data, or something more extreme, if the null hypothesis were true. So if male mice and female mice have the same average weight, what our p-value says is that there's between a 10 and 20% chance that just from random sampling, we would observe a difference of 5 grams between our samples. Okay, so we can get a 5-gram difference from random chance between 10 and 20% of the time, even when the null hypothesis is true. So even when this is true, we would get a 5-gram difference between 10 and 20% of the time.
Exactly 5 grams?
No, 5-gram difference or something larger than
Larger.
5 grams. Okay, so 5 grams or something larger, or negative 5 grams and something more negative. Okay, that's what that's saying. So what do you think? Do you think we can safely disregard that possibility and say this 5-gram difference is most likely a result of a difference in the population means? Or should we say it's very well possible that it happened from random chance? Okay, so I would say because our tail area, our p-value is between 10 and 20%, it's not small enough for me to just completely disregard. Okay, it's large enough for me to say I'm not ready to throw this possibility away. Okay. So p-value is between 0.10 and 0.20. Okay? So that means when the null hypothesis is true, I will observe data like mine or something more extreme. Between 0.10 and 0.20 of the time. Okay? That is not small enough for me to ignore or disregard. So I will not reject the possibility that the null hypothesis is true and my data happened by random chance alone. Yes?
How do you know that it's not small enough?
Yeah, okay, so I'll get to that, yes. That was going to be the same. Okay. So the question is, when do we say this is not small enough for me to ignore or disregard? Okay? And this is truly, this should be your judgment call as a researcher. Okay? You should be able to say, this number is, it can happen by random chance this much. I'm not ready to disregard that. Okay? It should be your call, but I guess historically, or just as time has gone on in this field, we have accepted 5% to be kind of our rule of thumb. If it can happen by random chance more than 5% of the time, generally we say, I'm not ready to disregard the possibility that it happened by random chance. So we will not reject the null hypothesis. However, if it happens less than 5% of the time from random chance, then we say, I'm ready to ignore the possibility that it happened by random chance, and I will reject the null hypothesis. Okay. I'll write that up on there. Okay. For better or worse, 5% has become the de facto standard. But truly, if you have a reason to use a different value to make your decision of whether you are ready to reject the null or not reject the null, that choice is yours. So, So notice I wrote, I will not reject the possibility that the null hypothesis is true, and that my data happened by random chance alone. Okay. Notice I am not writing, this proves that the null hypothesis is true. Okay, because it doesn't. We've looked at, whatever, 30 mice, 28 mice, and we did not find a statistically significant difference. That doesn't mean the averages of the two groups of mice are the same. It's just